The electrolysis of brine is a crucially important process in the chemical industry. The three primary products of electrolysis, namely chlorine, hydrogen and caustic soda, together with hydrochloric acid, sodium hypochlorite and other products derived from them, provide the building blocks for many processes, giving the northwest of England a vital role in British manufacturing. Products derived from brine are used in the manufacturing or processing of semiconductors, cleaning products, plastics, steel treatment, petrochemicals, water treatment, bleaching products, disinfectant, dyestuffs, medicine, weed killer, glass making, food production, PVC manufacture, tanning, sodium metal, soldering flux, textiles, paper making, laboratory reagents, detergents, rubber products, and many other items which you will find around your home today. Murgatroyd's brine well at Middlewich, with its seemingly inexhaustible supply of high-quality brine, was a valuable resource, and it had long been Murgatroyd's intention to expand their electrolysis capabilities. The plans had twice been interrupted by war, but immediately after World War II, the British government offered generous technical and financial assistance to companies who wished to develop their facilities. Murgatroyd took advantage of these offers to plan a completely new factory outside the town. The new company, initially known as the Murgatroyd Vacuum Salt Company, was formally incorporated on the 21st of May 1947, with a capital of £150,000. However, the scope of the project was soon widened to include production of caustic soda and other chemicals by electrolysis of the brine. A substantial loan was negotiated from the newly formed Finance Corporation for Industry, and the name of the company was changed to Murgatroyd's Salt and Chemical Company. This artist's impression shows the intended layout of the factory, which was to be situated between the A533 Middlewich to Sandbach Road and the adjacent railway, giving excellent transport facilities. It would have pipes for delivery of fuel and dispatch of bulk goods, while small quantities could be dispatched by road. From left to right we can see first the effluent treatment works, which was to ensure that no stray chemicals were discharged into the town sewerage system or the canal. The main site pumping station for moving brine and other chemicals on site, and for providing cooling water to and from the local canal. The cooling tower, which soon became a major landmark. The brine purification plant, with settling tanks in front. Then the brine filtration plant, where any residual impurities were removed. Then the vacuum salt production building. The salt warehouse, where the purified salt was stored, either for dispatch or further processing. Caustic, produced by electrolysis, was concentrated to 50% solution in this building and was sold as liquid caustic. Alternatively, caustic could be completely dried and sold in solid form, and the drying process took place in this building. Wet chlorine, straight from the electrolysis cells, is highly corrosive. In this unit it was dried and cooled to ambient temperature before being passed to the liquefaction plant. The heart of the factory was this long double building housing the hooker cells, in which brine was broken down into hydrogen, chlorine, and caustic soda. Next, the powerhouse. If you're wondering why the powerhouse and the cooling tower are opposite ends of the site, this is because exhaust steam from the turbines was used for processes in the intermediate buildings. The layout used reduced the lengths of pipe runs and the heat losses. Coal for the power station was delivered by train, using the sidings visible to the rear of the factory, and stored in this area. At the end of the site was the chlorine liquefaction plant. The dried chlorine was chilled, causing it to condense to its liquid form, then pumped into road or rail tankers in the adjacent loading bay. Some of the chlorine was reacted with hydrogen in this building to make hydrochloric acid. The final product was sodium hypochlorite, a powerful bleach, but not so hazardous to handle as liquid chlorine. This was produced here in the hypochlorite building. In addition to the production buildings were the workshops, where maintenance and repair operations were carried out. The office building was adjacent to the main entrance. And finally, there were staff canteen and welfare buildings. This layout was followed quite closely as the factory developed. The factory was built by Monk & Company, a builder from Warrington, and a photographic record of the construction was kept by the architects Sloane and Lloyd Barnes. Most of their photographs have survived and have been used as the basis of this presentation. They can now be found on the Middlewich Heritage Trust website, together with other archive materials relating to Middlewich life and industry. Brine was to be supplied from Murgatroyd's existing brine well at Middlewich. This source had been discovered by George Murgatroyd in 1889 and provided a copious quantity of high-purity brine until brine pumping was made illegal in 1977. The pump house is now a listed building, and the pumps are a scheduled monument. Both have recently been conserved by Middlewich Heritage Trust. A new pipeline was built to carry brine from the pumping station to the new Elworth factory. This photograph shows the pipeline under construction. The pipe itself is now long gone, but many of the concrete saddles can still be seen beside the railway. At the new factory, brine was stored in several large tanks, two of which can be seen in this picture. The steel skeleton was to become the brine purification plant, and the tall brick building was the vacuum evaporation plant. The building in the foreground was a central pumping station, which pumped water for the cooling tower to and from the nearby canal. Here we see the footings for the brine filtration plant, with the main pumping station behind and the effluent treatment works in the background. The two large tanks in the picture were to hold liquid caustic before and after treatment in the adjacent brick building. The steel skeleton in the foreground was to become the solid caustic building. The cooling tower can be seen in the background. Electrolysis requires huge quantities of energy. The production of 1 ton of caustic uses about as much electricity as an average modern house will consume in a year. The power station was designed to balance the electrical power output with output of steam to run the evaporators. 2 water tube boilers supplied steam to a turbine, which drove a 6.5 megawatt DC generator for the electrolysis cells and a 1.5 megawatt alternator for general factory power. exhaust steam from the turbine was used to heat the vacuum evaporators. Coal was brought in by rail to the company's new sidings, and cooling water was drawn from the nearby canal. This photograph of the turbine under construction shows the main steam control valves in the foreground, with the high-pressure turbine rotor behind. Beyond that is the low-pressure turbine casing awaiting its rotor. The two rotors would drive the large central gear, which in turn would drive a common output shaft. The bearings for this shaft and the lower casings for the three generators can be seen top right. The top half casings of both turbines, the gearbox and the first generator, are now in place. Looking from the other side, we can see all three generators in place. The turbines and gearbox are now fully lagged and have their outer covers in place, while the control panel is under construction on the right. There is even an operator on the floor below. Salt was produced by the vacuum process. But before I describe the process itself, there are a couple of things I need to explain. The first point relates to the way we define pressure. The normal atmospheric pressure around us is defined as 1 bar, short for barometric pressure. A hollow item with an opening in it, such as a bottle, is completely surrounded by air at a pressure of 1 bar, but also filled with air at the same pressure. So, if we take a new pressure gauge out of its box, it will show 0 pressure, because the pressure inside and outside are the same. This pressure is known as 0 bar gauge, or bar G for short. If we connect the gauge to a sealed vessel and pump air in, the pressure will rise. Conversely, if we pump air out, the pressure will fall, and the gauge will show negative pressure, or vacuum. Now, if our system normally works at very high pressure, this needn't worry us. But if the system works at pressures around atmospheric, all these positive and negative numbers can cause confusion when copying readings. If absolutely all the air is removed from our vessel, the pressure inside will be 0, and the gauge will now show -1 bar or 1 bar vacuum. Why not simply move the scale on the gauge to show 0 at this point? This is known as 0 bars absolute, or 0 bar A for short. Normal atmospheric pressure is 1 bar A, and what we normally think of as vacuum is any pressure between 0 and 1 bar. In the following description of the evaporation process, absolute pressures are used throughout. The second point concerning a kettle in your kitchen will boil when the water temperature reaches 100 degrees C. If you've ever used a pressure cooker, you will know that the higher pressure causes the water to boil at a higher temperature, thus cooking the food more quickly. Conversely, if you were to lower the pressure, the water would boil at a lower temperature. This is the principle behind the multi-stage evaporator system. In the vacuum salt process, brine is evaporated in tall vessels, partially filled with brine. A pump circulates the brine through a heat exchanger known as a calandria. The calandria is heated by steam from an external source, causing the brine to boil, and the condensed steam is drained off for reuse. As the brine boils, water vapour is drawn off from the top of the vessel and salt crystals settle to the bottom to form a slurry, shown here in red. The slurry is drawn off into a holding tank below, and fresh brine is added to maintain the liquid level inside the vessel. Each evaporator vessel is known as an effect. Hence, a plant with 4 vessels is known as a quadruple effect evaporator. The first effect is heated by exhaust steam from the turbines in the powerhouse, which arrives at a temperature of 126 degrees C, and heats the brine to 103 degrees C. If the pressure in the vessel is maintained at 1.12 bars, the brine will boil at 103 degrees C, and the vapour can be drawn off through the second calandria. This heats the second effect to 82 degrees C, and the pressure is reduced to 0.51 bars to make it boil. Vapour from the second effect heats the third effect to 62 degrees C, and it is boiled at a pressure of 0.22 bars. The fourth effect boils at 42 degrees C and a pressure of 0.07 bars, which is as low as reasonably practical. So vapour from the fourth effect is condensed and used elsewhere. Finally, a vacuum pump draws off any air which may have leaked into the system. To complete the picture, we must add the powerhouse, which supplies the steam. Condensate from the first effect is returned to the boiler feed system for reuse. Brine is fed from the brine holding tank to maintain liquid levels in the effects. The salt slurry is drained off and collected in a holding tank, from where it is passed through a drum filter. As brine is pumped from inside the drum, the salt crystals are retained on the outside, from where they are removed by a scraper. The brine is returned to the brine tank for reuse. The salt from the filter is dry enough for many purposes, and may be sold in this form as unstoved vacuum salt, but for ease of handling it may be stoved to form pure dried vacuum salt, or PDV salt for short. This photograph of the vacuum plant in operation shows how different it was from the clouds of vapour and hard manual labour associated with the open pan process. It was also much more efficient. An open pan could produce about 4 tons of salt for every ton of coal burnt, while a triple effect evaporator could produce 6 tons of salt, and a quadruple effect evaporator could produce 8 tons. Salt was stored in a large warehouse, ready either for dispatch or preparation for electrolysis. Because PDV salt was free-running, it could be delivered to industrial customers in bulk by road tankers and discharged using compressed air. Salt for domestic use was packed in small bags or boxes, which were then enclosed in larger boxes and dispatched in pallet loads using a normal vehicle. When they dissolve in water, many chemical compounds will separate into their component parts, each carrying an electric charge. For example, salt, sodium chloride, will separate into positively charged sodium and negatively charged chlorine. These charged particles are known as ions and can be removed by passing a direct electric current through the solution. 2 electrodes made of metal or other conducting material are connected to a power source. The one connected to the positive side of the supply is known as the anode, and the one connected to the negative side is called the cathode. The positive charge on the anode attracts the negative charge on the chlorine ions and chlorine is released as gas. Similarly, the negative cathode attracts the positive charge on the sodium, releasing sodium metal. However, sodium metal is extremely reactive and immediately reacts with the water to form sodium hydroxide, caustic soda, and hydrogen. The hydrogen is released as gas, and the caustic remains in solution. This diagram illustrates the complete process used in the factory. Salt for electrolysis was first dissolved in clean water to form saturated brine. Although the brine from Murgatroyds was of very high quality, even low levels of impurity in the salt would form insoluble deposits during the electrolysis process, gradually coating the electrodes and stopping the process. These impurities had to be removed before the brine could be used. To purify the brine, chemicals were added which reacted with the unwanted impurities to produce insoluble compounds. After thorough mixing, the brine was transferred to large tanks, where the impurities were allowed to settle. The brine was next filtered to remove any residual suspended material, and was then ready for use. The process of electrolysis separates the brine into sodium ions and chloride ions. These two ions are extremely reactive, so to prevent them recombining, the sodium ions are physically isolated from the chloride ions. The chloride ions combine in pairs to form chlorine gas, and the sodium ions are permitted to react with water to form sodium hydroxide, caustic soda, and hydrogen. There are several different electrolytic cell types, but the process is broadly similar in all three. Whichever type of cell is used, these three chemicals are produced in the same proportions, and it is therefore necessary for the manufacturer to have balanced markets for the different products. The hydrogen produced was dried and compressed for storage and distribution. Caustic was sold as a liquid at 50% concentration, or dried and sold in solid form. Wet chlorine is extremely corrosive, so the chlorine stream was dried before processing. It was then chilled to -34 degrees C, at which point it liquefied, and was then transported in its liquid form. Any residual chlorine in the depleted brine stream was reclaimed and added to the main chlorine stream. Finally, the depleted brine was returned to the saturation tank to be prepared for reuse. At Elworth, Hooker cells, named after the company who invented them, were used for the electrolysis. In a Hooker cell, a semi-permeable diaphragm separates the anode and the cathode. This diaphragm allows only the sodium ions to pass through, thereby isolating them from the chloride ions. Chlorine is liberated at the anode and is drawn off as a gas. At the cathode, hydrogen is liberated as a gas, and the remaining hydroxyl ion reacts with the sodium to give sodium hydroxide, or caustic soda. Pure water is added to replace that lost by electrolysis. The resultant caustic is at a concentration of about 33%, and the liquid must be evaporated to bring the concentration up to the commercial concentration of 50%, which was supplied under the name of liquid caustic. This photograph, taken from the railway, shows the Hooker cell room adjacent to the new company sidings. The caustic building is under construction beyond, then the salt evaporation building, and the cooling tower in the background. This interior view of the cell room shows the cells under construction. The carbon anodes are in place, awaiting the fitting of the cathodes and the top covers. In this photograph, we see the completed cells in operation. As an alternative to liquid caustic, some caustic was completely dried and supplied to customers in solid form. Here the drying and packing plant can be seen in the background, with drums of caustic in the foreground. Like all gases, chlorine occupies a large volume. So to make transport economically possible, it was liquefied to reduce the volume. This was done by cooling the gas below its boiling point and compressing it slightly. The liquid chlorine was then transferred to road or rail tankers designed to withstand the pressure of about 5.5 bars required to maintain it in the liquid state. The chlorine liquefaction building was placed at the end of the site, away from the other buildings, and had a ventilated roof in case of a chlorine leak inside the building. This photograph shows the chlorine chiller and compressor unit in operation. Murgatroyds had their own railway wagons for delivering large quantities of chlorine by the trainload, while smaller quantities were transported in road tankers. One very important product was sodium hypochlorite, widely used as a powerful bleaching agent. To produce this, chlorine is injected into caustic soda, and the resulting reaction yields sodium hypochlorite. Despite its powerful bleaching properties, sodium hypochlorite was more stable and much less hazardous to transport or use than liquid chlorine. Small quantities were supplied in 10-gallon glass jars, known as carboys, mounted in padded cages. Larger quantities were supplied in road or rail tankers. The availability of hydrogen and chlorine facilitated the production of high-grade hydrochloric acid. This is produced by burning chlorine in a hydrogen atmosphere, and forms the basic feedstock for many other industrial processes. Hydrogen gas was compressed to 200 bars and stored in relatively small diameter gas bottles. Because of the very high internal pressure, larger cylinders would have required very thick walls, making them too heavy for a vehicle to carry. It was therefore necessary to compromise between the capacity of the cylinders and the overall weight which could be carried on a road vehicle. Here we see a typical hydrogen delivery vehicle. Its rugged construction gives an indication of the weight of the gas bottles. Other chemicals could be stored at modest pressures and carried in standard road or rail vehicles. This photo shows assorted chemical tanker wagons standing on the company sidings, awaiting dispatch. As befits a state-of-the-art factory, a spacious reception area was included to impress visitors. This aerial photograph shows how close the completed works came to the original architect's impression. Demand for chemicals increased rapidly during the early years, and an additional cell room was built to increase production. Instead of hooker cells, mercury cells were chosen for the factory extension. The steel skeleton next to the hooker cell room is the new mercury cell room under construction. A second John Tom pump was installed in the Middlewich pump house in 1954 to meet the increasing demand for brine. The mercury cell has two chambers, an electrolyzer and a decomposer. Saturated brine is passed through the electrolyzer, and a stream of mercury flows across the base of the chamber. A metal plate anode is mounted above the mercury, and the stream of mercury forms the cathode. Chlorine gas is liberated at the anode and sodium at the cathode. Mercury has the property of being able to form alloys known as amalgams with other metals. As soon as sodium is formed on the surface of the mercury in the cell, it forms an amalgam, which is carried away by the mercury stream. Pure water is pumped upwards in the decomposer chamber through a bed of carbon granules. These ensure that the downward flowing mercury is broken into small droplets and brought into intimate contact with the water. Because sodium has a greater affinity for the water than it has for the mercury, the amalgam decomposes, and the sodium reacts with water to form caustic soda and hydrogen. The clean mercury is returned to pick up more sodium. The caustic produced is at the commercial concentration of 50%, and because of the cell construction, contains very little brine. This means that it requires minimal purification before use. The cells are also more efficient, meaning that less electricity is used in the electrolysis process. The individual cells were smaller than Hooker cells, giving the mercury cell room a more crowded appearance. The site reached its peak in the early 1970s, but once wild brine pumping was banned in 1977, a gradual decline set in. By 1999, the power station had gone. The green circle left of centre is the sump from the former cooling tower. Without the power station, there was no steam to heat the brine, so the brine evaporating plant has been removed, and the cell rooms are partially demolished. Hydrogen production continued for a few more years. The red objects on the left of the photograph are hydrogen delivery vehicles. By 2010, almost nothing of the original factory remained. By 2017, the site had been stripped. The land to the right is now being used for housing. This photo, taken from Albion Lock, shows the factory nearing completion in 1952. This recent photo, taken from the same position, shows how much has gone. We close with some film of the factory, starting with the pumping station at Middlewich, on which the prosperity of Murgatroyds was based from 1889 until 1977. One of the managers at the works was a keen cinephotographer and filmed many aspects of the works, both under construction and in operation. Unfortunately, he didn't record a commentary, and the quality of the films has suffered over the years, but what survives will give you a flavour of life at the factory in the early 50s. Especially what we would now regard as a very relaxed attitude to safety on site. Once it reached the Elworth factory, the brine was purified and stored in large tanks ready for use. We see two managers checking the tanks, then admiring a sample of the first purified brine produced at the factory. Production of the first salt caused much excitement, and we see both managers and staff hurrying to watch as some of the first vacuum salt comes off the drum filter. One of the managers demonstrates the free running qualities of this salt, and the section closes with a shot of the salt falling from the conveyor into the new salt warehouse. This sequence is followed by shots of two operators checking the output of the first hydrochloric acid to be produced at the new plant. Then, a sequence of pictures of road and rail tankers in the chlorine loading bay. A string of railway wagons illustrates the range of products and the quantities produced at the Elworth factory. And the video closes with shots of outgoing chlorine wagons and incoming coal wagons standing in the company sidings.